on this computer. Okay, we should be recording. And you should have the pad visible on your screen. And we'll start the screen share so that we can start the PowerPoint lesson for today. Okay, this is a second lesson on the Gibbs Free Energy. We've talked about the standard state Gibbs Free Energy for a reaction, and we made a very important point that the standard state gives a certain set of partial pressures for each substance in the mixture, and therefore is giving concentration based in mole fraction for everything that's involved in the reaction. Remember, the partial pressure of each component is 1 atmosphere pressure. The total pressure is the sum of the partial pressures of all of the gases involved in the reaction, both the reactants and the products. And then by Raoult's law, the mole fraction of any component is its partial pressure divided by the total pressure. So when we specify the standard state Gibbs free energy, we are giving the partial pressures of each component that's present in the solution. And we're also specifying the concentrations for each substance involved in the reaction. Now, the sign of delta G tells us whether a reaction is spontaneous or not. If we're talking about the delta G with the superscript, we can use that to decide which direction the reaction will shift in going from the standard state mixture to the equilibrium mixture. If delta G now without the superscript, it can be used to designate the free energy change for mixtures other than the standard state. So the one with the superscript means for one specific set of concentrations and partial pressures. Without the superscript means we can go into the lab and put any mixture together we want to and calculate the free energy of that mixture. If the sign of delta G is less than 0, then that means free energy comes out of the system, and that means it is spontaneous in the direction that you've written it. Remember, when you write down a reaction, what you've got on the left, you're saying is the reactants, and what you've got on the right, you're saying is the products. So if delta G for that reaction is less than 0 from whatever concentrations you have, then what you're going to get is reaction is to the right in the way you wrote the equation. But it's starting from a current mixture, not the standard mixture. If delta G is greater than 0, again without the superscript, then that means the reaction to the left is spontaneous, starting from current concentrations. Now you've got to start thinking about reactions as being able to go either direction. So even though we might conceptually set up a set of reactants and a set of products, things on the left to things on the right, we've got to remember that nature doesn't know what you wrote down. Nature's going to do what nature do, you know? And so it's going to go in the direction that lowers the free energy or releases free energy to the outside. Now, if delta G is equal to 0, you already are at equilibrium and nothing's going to happen. Now, okay. When we get the Q, remember Q is set up in the same way we do equilibrium constants, but it's putting in current values of the partial pressures. And K is the equilibrium values that we put in to evaluate K. Here is the relationship between the delta G with the superscript and the delta G without the superscript. Now, delta G with the superscript, remember now, we can calculate this thing from standard tables in the back of your textbook or in any other good handbook will have the value of the free energies of formation of substances. And we can calculate that delta G with the superscript from those tables. We know what the concentrations are that we've got in our reaction chamber. So we can calculate the Q. The Q would be just like the equilibrium constant, but we're going to put in the current pressures that we have in our mixture. R is the usual value, but now remember, in thermodynamics, the R is the 8.314 value, not the 0.0821. I've told you when you remember those constants, remember the units. The 8.314 is joules per mole per Kelvin, joules per mole per degree Kelvin, yes. The 0.0821 is liter atmospheres per mole per degree Kelvin. So if we're going to have delta G in joules, we've got to use R in its joule value as well. Now, since the equilibrium constant equals 0, when delta G equals 0, I can put a 0 on the left here. The Q will be equal to the Kp value when there's no change in equilibrium. You are at equilibrium when delta G is equal to 0. So Q at that point, the concentrations you have at that point, will be the equilibrium concentrations. So I can go up here and I plug in a 0 there. I get delta G equal minus RT log Q it would be, but Q is Kp. This is beautiful. This is really great because look what it told me I could do. I can measure the equilibrium constant by getting the delta G's out of the back of the book. Now, how great is that? You don't have to go to lab and do any chemistry at all if you're interested in calculating the Kp for a reaction, any old reaction you want to imagine. Just go to the back of the book, calculate delta G superscript, put in the temperature. Now the temperature is 298. We'll look later on how you would adjust this for some other temperature. Maybe your lab isn't at 25 degrees. So we can fix that, but don't just put the 25 in right here. Or the other temperature, okay? The temperature that has to go in this equation is 298.15 degrees Kelvin. R is 8.314. So this equation is really, really one of the high points of Gen Chem 2. Now, delta G superscript can be calculated from the tables, and we get the value of Kp without doing the experiment. Now, the Kp values at temperatures other than 25 degrees, you can use the Gibbs-Helmholtz equation. Delta G is delta H minus T delta S. Now, when you change temperatures, the heat of the reactants and the heat of delta H of the reactants and the delta S of the reactants would be lower than they would at a higher temperature. We go to a higher temperature, delta H, the enthalpy of the reactants and the enthalpy of the products would both increase with temperature. But the delta H, the difference between them, doesn't change much. So what we can do is use the delta H and delta S values directly out of the table again for 25 degrees. We can put these values in from that table calculation and our new temperature here, and we get a pretty good estimate of delta G at some other temperature. So we are using the delta H and delta S from the tables at 25 degrees and calculate delta G at some temperature other than 25 degrees. We put our new temperature in kelvins in and get delta G at a big higher temperature or different temperature. Okay, now, here's some problems. We're going to define the standard state, calculate delta H, delta S, and delta G for this reaction. And I've deliberately picked a really interesting reaction. Hey, I would love to be able to take carbon, graphite, charcoal, put a little hydrogen with it that's really, really cheap. It's easy to make, electrolysis, or you can buy it from suppliers that you get it from in manufacturing of gasoline. Is we get a lot of hydrogen coming off in that process. And by the way, a lot of people believe we get hydrogen from electrolysis of water. We absolutely do not. It costs too much to make it that way. It's a byproduct, a quote, waste product when we make gasoline. And we get our hydrogen. If you go order a tank of hydrogen, it was made by using crude oil. So just so you know, if you are burning hydrogen in your car to do the green thing, you are not doing the green thing. You are using hydrogen that's made from crude oil. So you may as well burn the crude oil instead. It's not going to make much difference. But this would be a great reaction if we could do it. Take carbon and hydrogen, both cheap, and make methane, the natural gas you use in your Bunsen burner. Now your car will run on that. That would be a really good thing. It's still not going to be, quote, green. It's still going to have the hydrogen made from crude oil, at least for now. All right, so there's the reaction. Now let's think about the standard state. We've got to have all of the stuff present. So it should be in the form of graphite. It doesn't really matter how much you have because it's a solid. As long as there's a speck in that mixture, that reaction can continue to occur. Now, should that be a limiting reagent, you would use it up and then the reaction would stop. But as long as you've got a speck of carbon there, that will work in the standard state. You've got to have hydrogen at 1 atmosphere pressure, not 2, 1 atmosphere pressure, and 1 atmosphere of CH4. To define the standard state, you do have to have the products present too, okay? And it has to be at 25 degrees C to be our standard state in this country. Now, the delta H of the reaction is the products minus the reactants. So we've got 1 mole of CH4, and we'll take 1 times the delta H of formation of CH4. That should be a minus. Minus 2 times the, let's see, oh no, I'm sorry. I was right. The delta H of formation of CH4 is minus 74.8 kilojoules per mole. So if I got 1 mole, the delta H is minus 74.8 kilojoules. The delta S is going to be the delta S of the reaction is going to be the delta S, the third law entropy of CH4, there's 1 mole, minus twice the third law entropy of hydrogen, minus once the third law entropy of CH4. Okay, so here's the data. Delta S is negative 80.55. I guess since we've not done this reaction, we don't really know for sure whether it ought to be exothermic or endothermic. But I can tell you that reactions of most anything with hydrogen is an exothermic process, and that is what we observed. And what about the entropy of the reaction? Well, we've got 1 mole of gas product and 2 moles of gaseous reactant. So delta N is minus 1. So delta S should have the same sign as delta N, negative, and it does. So as we check our values, this looks right. We get delta G is delta H minus T delta S. There is the values that we got for delta H. there's the value that we got for delta S. Now notice S is going to come out in joules per mole per Kelvin, or in the case of a reaction, just joules per Kelvin. And we need it in kilojoules if we're going to add the two together, or in this case, subtract the two. They still have to have the same units. So either you have to change the delta H to joules, or change the delta S to kilojoules. Now I changed the delta S in this PowerPoint lesson to kilojoules. Normally, I wouldn't do it that way. I'd probably change the delta H into joules. But, you know, it's 6 of one and a half a dozen of the other. Pick whichever way you want to do it. It doesn't matter. Just be sure the units are the same. Always carry the units with you when you do these calculations. So I'm calculating delta H, or delta G, at 298 to be minus 50.84. And the true value from the table values is, you know, taking delta G of formation of products minus reactants, is minus 50.72. Now, generally, we don't expect perfect agreement with this, especially when you're involving solids in the reaction. Getting the entropy of solids is not terribly easy to do and involves some error. So very often you will see the delta S of, or the entropy of carbon as a solid. If you look at your tables periodically, you'll see that they typically do change that value every once in a while. Okay, now, will a mixture of 1 gram of carbon, 2 atmospheres of hydrogen, and 1 atmosphere of CH4 be at equilibrium? Well, there's my reaction again. If not, which direction will the reaction shift in reaching equilibrium? Well, we're going to use this equation and calculate delta G. Delta G is delta G superscript plus RT ln of Q. So there is the delta G we calculated a while ago, minus 50.80 times 10 to the third joules. I changed that one now to get consistent with the units on R, 8.314 joules per mole per Kelvin. And the temperature is 25 degrees. Now, the Ln of Q is the partial pressure of the CH4, which is 1 atmosphere, divided by the partial pressure of hydrogen squared. There's 2 of them. And so we've got it set up now to do the math. We get minus 54.26 kilojoules would be the delta G of this reaction. Now, it did become more favorable. So this mixture would be a little bit more spontaneous to the right and toward our product. So this would be a better mixture than the standard mixture would be in order to make that happen. Well, does that make sense? Let's look back up here. When we talked about the standard state, we had 1 atmosphere pressure here and 1 atmosphere pressure here. All the gases at 1 atmosphere. What if we add more hydrogen to this equilibrium? Le Chatelier says it should shift to the right. So that makes it go faster and better to the right. Well, not faster necessarily, but better to the right than it would at 1 atmosphere pressure. So these answers are consistent with Le Chatelier's principle and other things that we've already learned. That's one of the nice things about chemistry. You may learn different ways to do different things, but still got to be the same every direction you go. Now, since delta G is negative, it will be spontaneous to the right, as we said up there. Now, let's calculate delta G for this mixture that we have up here. We just did that calculation. Calculate Kp at 25 degrees and at 500 degrees Celsius. Would we get a better equilibrium constant if we raise the temperature? Okay, well, let's see. At equilibrium, delta G is going to be equal to 0. and delta G superscript is minus RT log Kp. We can plug in our data like that. We get minus our Ln and Kp is, I moved the minus sign to the other side, solving for Kp, minus delta G. And delta G was minus 50.8 times 10 to the third joules, divided by 8.314 joules per mole per Kelvin, and divided by 298 Kelvin. And if we evaluate that, we get the log of Kp is plus 20.504. If I raise both sides to the e power, that means that Kp is e to the 20.504, which is 8.03 times 10 to the 8th. That's a fairly nice equilibrium constant, even at 25 degrees. Now, what about at 500 degrees? Well, we got to calculate delta G superscript at 500. And so what we're going to do is delta G superscript is delta H minus T. 500 Kelvin is 773.15 times delta S, which is minus 80.8. And we get delta G at 500 degrees as minus 12.34 kilojoules. And if we then rearrange and solve, we get Kp to be 6.8. So if we raise the temperature, it's not going to do good for us. Okay, well, what did we say? The reaction was exothermic, right? Which means if you raise the temperature, Le Chatelier says it'll shift to the left, which means it's going to reduce the equilibrium constant. Hey, look, that's what we got. But now we got numbers. It was this value at 25 degrees. It's only 6.8 at 500 degrees Celsius. Do these values agree with expected changes in Kp as temperatures increase? Well, we just showed it did. It was exothermic, so it'll shift left if the temperatures increase. Okay, so Kp should decrease. And that's what we observe. Now calculate a temperature at which the equilibrium constant Kp would equal 1. Well, there's our relationship. Delta G is minus RT ln of Kp. Now, if I want the ln to be equal to 1, then the log of 1 is 0. So I want delta G superscript to be equal to 0 at some temperature. And there's my delta H and delta S. Now, delta G needs to be 0. So delta H minus T delta S is equal to 0. I can solve for the temperature. It's delta H divided by delta S. And if I had minus 74.8 kilojoules, delta S was minus 0.08055 kilojoules per degree. So if I solve for that, I get the temperature is 928.6 degrees, where we would get to an equilibrium constant equal to 1. That would be 655.6 degrees Celsius. So that's the temperature at which this equilibrium constant equals 1. It's sort of the break-even point. You're going to get essentially 50% reaction toward products. Okay. Now, calculate the equilibrium vapor pressure of water at 25 degrees. Well, let's see if we can do that. There's the reaction for water, liquid, going to water, gaseous. Kp is the partial pressure of the water at equilibrium divided by, this is a liquid, so we don't include liquids in the equilibrium Kp expression. We're only doing pressures. Okay, so delta G is minus RT log Kp, and delta G is minus RT log of the vapor pressure of water at equilibrium. And delta G is delta H of the gas minus the delta G of the liquid. And here are the numbers. So delta G superscript is minus 228.57 minus a minus 237.13 kilojoules. And so delta G is plus 8.56 kilojoules. Now, I've got the numbers I need. the log of Kp is going to be 8.56 times 10 to the third. Remember, you have to convert from kilo joules to joules, and we do that by replacing the K with what it's equal to, 10 to the third. I want to divide that by 8.314 times 298. That's the temperature we wanted the vapor pressure at. We get log of the vapor pressure is minus 3.25. That's going to be vapor pressure. Then if I raise both sides to the E power, E to the minus 3.455 is 0.0316 atmospheres. We convert from atmospheres 760, 1 atmosphere is 760 torr. So the value that we calculate is 24.0 torr. And the table value, hey, we do pretty good there. And we get the table value is 23.8. The measured vapor pressure of water at 25 degrees measured in the laboratory is 23.8. We calculated and didn't even go to the laboratory, 24.0. Hey, I'm for that. Okay, now here's a checkpoint problem for you. It's the formation of ammonia. Again, a very important reaction. The delta G superscript for the reaction, it's just going to be twice the delta G of formation of ammonia. Remember, N2 and H2 are both 0. So this is the delta G of the reaction we would look up in the table by getting delta G of formation of ammonia and multiplying by 2. We get minus 32.9 kilojoules. Calculate the equilibrium constant. Calculate the delta G for the mixture composed of 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 2 atmospheres of ammonia. We're going to put those values in and calculate delta G for that mixture. Now, here's another one. You've got this information. There's again, the vaporization of water. Delta H for the vaporization is plus 44.01 kilojoules. Delta S for that is plus 118.9. Well, over here, let's see, do these make sense? If I'm going to take liquid water and boil it, make a gas out of it, I have to put heat into it, don't I, to boil it? Sign ought to be positive. Okay, this is a gas. It has a lot more entropy than liquid water does. Or water molecules are much more organized than gaseous molecules are. So the disorder increases. That should be positive, and it is. We're given the Kp is just going to be the partial pressure of the water. Delta G superscript is minus RT log Kp. Delta G superscript is delta H minus T delta S. And at the boiling point, partial pressure of water will be 1 atmosphere. Follow the pattern we did on the vapor pressure. And at the boiling point, the temperature is going to be 1 atmosphere. So we'll know what that pressure is. You can calculate that. Calculate the expected boiling point of water. And that sort of covers everything that we needed to do in this lecture, and all the material that is actually on your quiz on Friday. Okay, now I'm going to stop the recording here, and okay, I'm going to stop the recording.